Before I start, I just want to just follow up on what Bill said. So when I was, I think in grade 10 or so, because I take this computer science course, and as Bill said, he didn't know very much about it, and most of the students knew more than he did. And I think to his credit, he said, just go for it. See what you can do with it. And that really introduced me to kind of the excitement of kind of doing stuff which no one's ever done before, rather than just looking stuff out of a book. And so that experience, that computer science class, really kind of, I found this love of just doing research and just explaining and presenting new things. So I give a lot of credit to Bill, actually, for awakening that in me, because before then I was just, I don't know, it just wasn't, school wasn't that interesting, but he really made it interesting to me, and so the rest is kind of history. And so what I want to talk about today is about climate change, and most of you in the audience will probably recognize this image. If they're on here. Yeah, so this is, actually this is an animation of Earthrise when Apollo 8 on Christmas Eve 1968 came over from the dark side of the moon, and then for one of the first times we as humans could see our Earth from a distance, and what we sort of saw was this wonderful blue marble kind of sitting out in kind of the coldness of space, and especially if you compare it to, you know, the moon sort of in the foreground, which is an incredibly kind of dead place. We really saw how unique the Earth was, and so I think this is something I'll come back to, you know, throughout this talk, is that the Earth is a very, very special place, and there's only one of them, and we have to make sure that we are good stewards of it and pass it on to future generations in a way, in fact, that it was passed on to us. And so I think this is really quite a seminal image in sort of the history of humankind. And so I'm a physicist, so most of you think physicists either study the Higgs boson or do something with quantum mechanics or gravitational waves. But I'm a classical physicist, so I use the physics that Newton discovered in the 17th century to try to understand how the fluid, and there's actually two fluids that make up mainly the climate system. There's the Earth and there's the ocean. So I try to understand, using classical physics, how those two fluids interact. And so that's sort of what I do. I do a bunch of different things. I'll talk briefly about some work I do with ice cores, because one of the problems we have in the climate system is we only have about 50 years of really, really good climate data. And so, of course, to put the changes that we're seeing now into context, one needs longer records to do that. And so one of the ways we do that is we look at past climate, and we have proxies like ice cores, tree rings that we can use to infer past climate variability and past changes. That allows us to put things into context. I also fly planes into storms. I don't fly, I just sit in the back of the plane, and they're mostly over the polar ocean, studying the transfer between the two fluids of the ocean and the atmosphere. And so I've been fortunate to see a lot of pretty amazing things during my career, and I'll sort of try to intersperse some of that stuff through this talk. And so what I want to do, I want to introduce the science of climate change. So what is really the science behind the fact that we're changing our climate, and then how you guys can be more informed citizens. Because I think one of the problems is there's lots of noise out there. There's lots of people with agendas, be it the coal industry or Donald Trump or whoever. And so I think it's important to kind of understand really what people are trying to say and what is really the core message behind climate change. So this is an example actually of a whale, humpback whale. Jane actually was on this trip with me to, this is to West Greenland, a place called Disco Bay. Pretty cool to me. And that's an iceberg in the background. That iceberg is probably about 500 meters long, maybe above water, maybe 50 meters, and of course it goes down probably 900 meters below. So it's a really, really big chunk of ice. And these things are floating all around that region. We followed this whale for about an hour. It was just porpoising along, and the captain of the boat was trying to kind of follow it. And suddenly it dove down to the bottom and showed its fluke, and then it went down to the bottom, and that was the end of that. So these are some of the kind of cool things that I've been fortunate to see in my career. So to start off, then I want to just make an important point of the difference between weather and climate. Now, you know the difference between weather and climate? Yeah?
I'd say weather is temporary, climate is long-term.
That's a great way to do it. So we kind of say climate is what you expect, and weather is what you get. So if you think of this as being temperature, for instance, then this is time, then essentially these wiggles are the weather. Some days it's warm, some days it's cold. In this case, the green line would then be the average, and that would be sort of the climate. Okay, so the weather is the wiggles, the climate is sort of the average. And of course, one kind of more complicated cases, this might be summer and winter. So of course, we expect our winters to be cold. And so they're cold, summers be warm. But even in the middle of winter, one can get warm days. And of course, in the middle of summer, one can get cold days. So we don't freak out if, in the middle of July, it goes down to maybe 10 degrees Celsius. That's just maybe a bit unusual, but it's not totally out of the question. And similarly, in the winter, it can get above freezing. So we sometimes have those kinds of cycles. And this could also be some longer-term cycle, because one of the things that happens in the climate system is one has variability on all kinds of time scales. And this could be maybe 20 or 30 years. So maybe for a few years it's cold, and then it's kind of just gradually warm, and then it's kind of gradually cold again. So there's many time scales upon which variability happens in the atmosphere. And again, this is one of the problems we have in trying to characterize things. If we're in just a situation here, we might say, oh no, the climate's warming up. But of course, it's just part of a longer-term cycle, and it may cool down. So when we talk about climate change and global warming, we have to kind of make sure that we're not seeing just some kind of variability, maybe on timescales of a few decades or so. We're actually looking at something which is really a trend, rather than just variability. So this is one of the problems with understanding the climate systems. We have all kinds of variability, and sometimes it's hard to kind of look at trends compared to variability. So what is a climate system? Well, essentially it's everything. It's the ocean, the atmosphere, what we call the cryosphere, which is our glaciers on land, sea ice over the ocean, the land surface, the biosphere. There's a strong interaction between the climate system and vegetation, so that's part of the climate system. And then all the interactions between those various parts of the system. So the climate system essentially is everything. Energy is being fluxed between the ocean and the atmosphere, between the land surface and the ocean, etc. And so we essentially need to understand all these processes if we're going to understand the climate system and how it's changing. So that's one of the real complexities, is there's many interactions going on, and we essentially have to study all those interactions to really understand how the climate is behaving. So what's climate variability? Well, it's essentially any change in any parameter on any length scale or time scale that you want. This is Nathan Phillips squared in the summertime, and Nathan Phillips squared in the wintertime. So that's an example of climate variability. Again, we expect our winters to be cold and our summers to be warm. This is actually a picture of Mount Logan. So one of the places where I work is Mount Logan in the Yukon Territory. It's the highest mountain in Canada. And we extracted an ice core from 5,000 meters high on this mountain. This is a record now going back to the middle of the 18th century, around 1730, of the snow accumulation every year from this ice core. So it turns out the snow accumulation in an ice core is kind of like a tree ring. Every year there's an annual amount of snow that falls, and you can actually see clearly the year-to-year snow accumulation, and such that you can count backwards and see some years there's lots of snow accumulating, some years there's not so much snow accumulating. And this is a record then annually running from 1730 to about the year 2000. And you see there's lots of variability. Some years there's lots of snow accumulating on the mountain. Sometimes there's not very much snow accumulating on the mountain. And that's an example of sort of variability. If you kind of look at more detail, what you can see is that for the first about 100 years or so of this record, there is variability, but the average or the mean is approximately constant. Okay, so this is a situation where the amount of snow accumulating may change from year to year, but on average it was always about, in this case, about 0.35 meters of snow every year. Then around 1850 something happened, and superimposed on this variability, there actually is a trend towards higher snow accumulation. Okay? So even though, again, here you're getting some years where there's more snow accumulating, some years there's less, on average, year over year, you're actually getting more snow accumulating on the mountain. And so this is an example of a trend in the climate system. This isn't just some sort of low-frequency variability. We think it's actually a trend, and we think it's related actually to the warming that's happening in the climate system. So around 1850 was when we started burning fossil fuels, and so we think this is actually a signature of, in fact, the anthropogenic climate change that is being induced by our use of carbon. So that's an example of how you can use an ice core to reconstruct past climate. This is a record of surface temperature. I've shown the global record, the northern hemisphere, and 60 to 90 degrees north. This data set starts in 1900, so it's about 120 years or so of data. And again, you can see there are fluctuations from year to year. Some years it's warmer, some years it's colder, but on average over this 120-year period, there's definitely been a warming in the climate system. Okay, and this is exactly the same kind of process that we saw in the ice core. This is a signature of anthropogenic climate change. If you look carefully, you'll notice that the blue curve, which essentially is the Arctic, this is the area north of 64 degrees north, recently has been warming at a much higher rate than the rest of the planet. Okay? And so for instance, northern Canada is warming much more rapidly than the rest of the planet, and that's because of what's called a positive feedback loop in the climate system. And so a positive feedback loop is what would happen if I brought this microphone to the speaker. You would hear that ringing noise quite quickly, amplifying. So what happens is there's noise in this system. When I bring it close to the amplifier of the speaker, that noise is amplified, and that's why you suddenly get that ringing noise. Okay? So what we think is happening in the Arctic is exactly the same thing. There's a positive feedback loop, where as we essentially warm the climate up, we're melting sea ice back. And so we're replacing very bright sea ice with very, very dark ocean. And that darker ocean absorbs more solar radiation, and that warms up the area more, and melts more sea ice, and that's a positive feedback loop. So we'll come back to this at the end. So there is this data shows that the Arctic is warming at a more rapid rate than the rest of the Earth. And this is a big problem for Canada, because of course we're an Arctic nation. And so we will be sort of seeing in the north, I'm not talking about here, I'm talking about in the north, an amplification of the warming, which will have impacts on the indigenous people who live there, and also the use of, for instance, the Northwest Passage as a maritime route may in fact be enhanced because of this amplified warming that's happening in high latitudes. So one of the other ways that we sort of understand climate change is we can look at photographs of things like glaciers in the past and see how these glaciers have changed over time. This is a Google image. Essentially, this is southwest Greenland. Nuuk, the capital of Greenland, is down here. And there's actually a number of different ice sheets actually on Greenland. This over here, what I call GRIS, is the main Greenland ice sheet. That's the one that covers essentially the whole island. But there's a small little ice cap called the Sukkertoppen ice cap, which exists in this region here, and there's actually a valley that separates this ice cap from the rest of the Greenland ice sheet. So it's a unique ice sheet in Greenland. And this is a picture taken in the 1930s of this valley, so this fjord here that goes between these two ice caps. This is a picture in the 1930s. This is the Greenland ice sheet on this side. The Sukkertoppen ice cap is on this side here. And it's this very, very large glacier that fills this whole valley, this whole fjord, with some open water down here. Now, if you look at a picture today, this is in 2013, from essentially the same vantage point, it's really changed. That glacier, which filled this whole valley, is now gone. It's now replaced by open water. Okay? And you can even see some indications of some of the glaciers that flow down into this valley have actually changed over time. Okay? So this is sort of a dramatic photographic evidence of the changes that have been happening in this part of Greenland over the last 50 or 60 years. And this is a really, ice caps and glaciers are really important parts of the climate system because they respond on very, very long time scales. So if you see a change like this happening, that's not because it's just become warmer for a few years. This is to see a change in a glacier, you need continued warming for decades and decades and decades. So glaciers respond on very, very long time scales. And so if you see a change in a glacier, like this retreat here, you know that's because there's been a warming, which has gone on for many, many, many years. It's not just a few random warm years that have done that. This is many, many years. So this is, if you like, very powerful photographic evidence, again, of how the climate is changing. Now, this is looking at a very, very long record. This is going back 65 million years. So here we have 65 million years of climate change. And, the Earth actually, back in the around 50 million years ago, actually was quite warm. It kind of cooled down for a while, and it's actually continued to cool down. This is a very interesting time. It's the Eocene optimum. And what we think happened at this time is that there was a huge outgassing of methane from the ocean. So methane is a very, very powerful greenhouse gas. and essentially it was very, very warm at that period of time, mostly because of this outgassing of methane. And this period, around 55 million years ago, was a very interesting time, because this was the warmest that it's been in the last 65 million years. It was actually much, much warmer than it is today, and that's because the sun was more powerful then, the continents were a different configuration. There was this mass outgassing of methane. And what I have here, you guys can go afterwards and see this. This actually is a piece of wood, which is 55 million years old. And it's actually wood. It's not petrified. You can burn this. And a few years ago, a colleague of mine came into my office with this piece of wood. He said, "Look at this, Kent." And I said, "It looks actually pretty cool." He says, "How old do you think it is?" I said, "I don't know, maybe 100 years old. It looked pretty old." He said, "No, it's 55 million years old." And that was kind of blew my mind. And what actually happened is this actually comes from one of the diamond mines up in the Northwest Territories. And so diamond mines form where there's what's called a kimberlite pipe development. And what a kimberlite pipe is, it's just a very, very mild volcanic eruption. It's not like Pinatubo where it kind of spews huge amounts of gas up. It's a very, very gentle volcanic eruption, and it brings diamonds from deep in the core up towards the surface. And so all the diamond mines in the world are all around these kimberlite pipes. And this is the diamond mine in the Northwest Territories. And so my colleague had a student who was working in that diamond mine, and when they were uncovering this pit here, they came across a huge forest of this wood. Okay, and so what they think happened was, again, when this kimberlite pipe exploded about 55 million years ago, there actually was a redwood forest growing in the Northwest Territories. Again, it was really, really warm back there. And this forest was essentially covered by the eruption, and it was in such a state that it never actually petrified, it just remained wood. And so what Dan got from that diamond mine was, we have boxes and boxes of this stuff, and it's all 55 million years old. They know how old it is because they can date it from the diamonds that are here, okay? And why this is important is that we can actually use this wood. There's annual growth rates in this wood. And so we can actually go back and see how the climate was varying from year to year back at this time when the Earth was really, really, really warm. And so that's one of the things we're actually doing with this wood, is trying to understand climate variability back 55 million years ago, in a time when the Earth was very, very warm, much warmer than it is today. And hopefully that'll give us some indication as to what's happening today. So that's actually what a redwood or a sequoia tree looks like. And these things were growing in the Northwest Territories 55 million years ago. Okay? And so that wood is pretty amazing, and it's an example again of climate change. So again, we're not saying the Earth is as warm. I mean, the Earth has been warmer than it is today. The problem is 55 million years ago, it wasn't because the humans or the dinosaurs or whoever was living there was burning carbon. It was some natural kind of outcome of the way that the climate system was set up at that time. And so it's a bit different than today, because clearly today we're the ones that are forcing climate change. But there have been times in the past when the Earth has been very, very warm, much, much warmer than it is today. So afterwards, you have a look at this. It's actually quite amazing. I think it's probably one of the most amazing things I've ever held in my hand, other than my children. And it really just kind of shows you really how kind of amazingly complicated and also how amazingly interesting the climate system is. So this is an animation of sea ice. So sea ice is kind of like glaciers. When you see changes in sea ice over long periods of time, you can see again that's an indication of the climate changing. And so this is an animation. So 1979 was when we have our best records of sea ice in the Arctic. And you can see 1979, it's been going down. There's an annual pulsation here. So the sea ice always extends outwards in the winter, and it retreats back in the summer. But over this 30 or 40 year period, there's definitely been a reduction in the amount of sea ice in the Arctic, and it's another indication of the fact that the climate is changing. Again, this isn't 1 year. There are years where it's high, years where it's low. That's the kind of natural variability. Just like here we have some warm summers, some cold summers, warm winters, cold winters. That's just the natural variability in the system. But there is this trend over this 30, 40 year period of a decrease in sea ice. Okay? And this again is another indication that we're seeing a change in the climate. So sea ice is like a glacier, and when you see a change in that, you definitely are seeing an impact of a long-term warming of the climate system. So I really want to talk about something which was just came up actually last week. So this is a satellite image of, so the National Geographic wrote an article on it. I was on As It Happens, talking about it last week. I was in the Sydney Morning Herald. I think they told me at the University of Toronto the website was broken or some number of people kind of looking at this kind of stuff. And so this is a satellite image. Now we're in Antarctica, not in the Arctic, we're in Antarctica. And so this is the Antarctic continent here. This is around 0 degrees. So essentially if you went due south from England, eventually we get to this region here. So in Antarctica, unlike the Arctic, there's a continent at the South Pole, and the sea ice grows out from the continent. And so it grows out in the winter and it melts back totally in the summer. So there's no multi-year ice in Antarctica, it's all first-year ice. And so this is essentially a picture taken a few days ago, and the blue curve shows you the ice edge. So this is all open water up here. This is the Antarctic continent, and usually you have just pack ice in Antarctica. But around a month ago, an area called the Polynya opened up in this region. And this is about the size of maybe Maine or New Brunswick or maybe Lake Huron at this time. So it's a really, really huge area of open water deep in the ice pack. Okay? And it turns out this thing hasn't really, in the 1970s, there was a very, very large Polynya. This is the same region now. This is actually a sea ice concentration map from the 1970s. This is all done by satellite. And so the blue area essentially is open water. And we'll come back to this little area here. That's actually the area around this Polynya right here. And so in the 1970s, for 3 years, there was a very, very large Polynya, probably about 400,000 square kilometers, so huge, 4 times the size of Lake Superior, huge area of open water. And then it went away. We didn't really see it again until 2016. And that's actually why people were so interested in this. This is now something that's come back after being absent for about 40 years. It's kind of interesting is that, in fact, the first satellite that was able to measure sea ice concentration from space was actually launched in 1973. Okay? And so had that satellite been launched a few years later, we would never have known this thing was actually there. Because you can't see it from the edge of the ice. It's deep in the ice pack. The only way you actually can see it is from space. So it's quite fortuitous that we put the satellite up in the 70s. Had we not put it up, we would actually have never known that it was there. That again just shows you how little we know about the climate system. We could have missed something 400,000 square kilometer area of open water just because we didn't have any way to actually visualize it or actually sense it from space. And so this is a record of sea ice, the area of open water in this region right here, the last 2 years. So the red curve here is 2016, and the blue curve is 2017. So in 2016, after 40 years, the Polynya came back. It had an area of maybe 40,000 square kilometers or so. This year, when we were quite excited about this opening, and we kind of joked, what'll happen when it comes back next year? And sure enough, next year it came back much, much higher. So at its peak was about 80,000 square kilometers. So a very, very large area of open water. It opened up actually almost in just a few days. So it went essentially from essentially 100% ice cover to essentially an area the size of Lake Superior that's open water in just a few days. So it's a very, very dramatic opening. We kind of have an idea what's happening. We're really not 100% sure why this thing opened up. And so actually one of the questions I was asked actually on As It Happens was, what impact does this have on the biology? Okay? And so we know from the Arctic, when these Polynyas open up, they're an area of huge biological activity. All the seals congregate there because it's easier to breathe. The polar bears go because the seals are there, you know, and et cetera, et cetera, et cetera. So they're very, very active biologically. And so one of the questions that Carol Loff asked me is what happens in the Antarctic? And I kind of fluffed an answer a little bit, but I actually went back afterwards and actually looked at that. So this is another satellite image. And that's the Polynya there. But these green colorings actually are areas where there's lots of biological activity happening in the ocean. And these actually are phytoplankton blooms. So phytoplankton is an algae, single-celled algae, which can grow when there's sunlight present. Okay? And so normally these phytoplankton blooms occur when the ice melts back, because then essentially when it's open water, and the algae can essentially synthesize chlorophyll and grow. what's happening within this polynya is it's really, really green there. And so there's actually lots of biological activity happening in this polynya. So these algae are just sitting there in a dormant state. As soon as there's sunlight, they start to grow. Okay, so these algae are taking advantage of the fact that this polynya is open water. Okay, so again, deep in the ice pack, there's this open water, and so the biology is kicking in. They don't care whether it should be there or not. They're just going to photosynthesize and grow. So these algae actually are growing within this polynya. Now you might say, why can't you see areas otherwise? Well, it turns out that when there's clouds present, you can't obviously see the surface, and so we can't actually infer biological activity when there's clouds around. So most of this area off of Antarctica is all open water, but you don't see any evidence of biological activity because there's cloud. But there's actually some open water here, some cloudy-free region here. And you can see this kind of green color here. So there actually is biological activity happening here. But here it's also happening deep in the ice pack. Okay, and this is another example of sort of the biology is taking advantage of the changes in climate. And so this is one thing that happens. Insects are now starting to colonize places in the Arctic where people have never seen insects before. There's a concern that, for instance, in places in Africa, high up like Nairobi or Kampala, places that are generally resistant to malaria and things, malaria may become more common as the mosquito vectors can now live in those regions because it's getting warmer. And so, of course, the biology will take advantage of anything that it can, and this is an example of one of the maybe positive things that biology is happening, but there's also negative changes as well. So this again gives you a sense that the system is very coupled, it's very complicated, and the biology is going to take advantage of any changes that are actually happening. So we talk about the greenhouse effect. So it turns out that John Tyndall was an Irish physicist, rather dour-looking guy here, and in the 1850s, he developed this instrument. Actually, it was at one of his at a centenary of his death a few years ago. And they actually had this instrument. It was a really complicated piece of equipment, okay, built in the 1850s. And what he could do with this is he actually could put essentially some gas in this column, in this tube here. And he could shine light through that tube. And he could see how much of that light was absorbed in the tube and how much was actually transmitted through. Why he did this, I don't know. That's the one thing about science, is people do things and they get interesting results. So what he did, he had this tube here, and it had an infrared light. So he had a light, essentially, that emitted not visible radiation like we see, but infrared radiation, like the radiation you get from your heating elements on your stove when you turn them really high. You see that kind of dull red that glows there? That's actually infrared radiation. So he had some source of infrared radiation. He could put gases in this tube, and he could see what happens. So when he put water vapor and carbon dioxide in that tube, he found that the infrared radiation was actually absorbed by those gases. When he put oxygen, nitrogen, nothing happened. Okay? So from this, he was able to discover what we call the greenhouse effect, and that is that infrared radiation can be absorbed by gases like carbon dioxide and water vapor. And of course, the greenhouse effect works because the radiation from the Earth is infrared radiation. And so what's happening is that some of that energy is being trapped in the system and then being radiated back down towards the surface, just like a blanket would. And that's why essentially the Earth is warming up, is because we're increasing the amount of carbon dioxide. So actually, Tyndall concluded from this that if we didn't have water vapor and carbon dioxide in the atmosphere, he said the Earth would be held fast in the iron grip of frost. So he, back in the 1850s, he understood that if there was no carbon dioxide and no water vapor in the atmosphere, the Earth would be a very, very cold place. The average surface temperature would be maybe minus 30 degrees Celsius. Okay, so we wouldn't exist because our biology requires water in a liquid form. And so clearly what's happened is that these greenhouse gases warm the planet up. Part of that is good, because without those gases, we would of course be minus 30, we wouldn't be here. And that warming essentially has allowed us to exist. But the problem, of course, is that now we're adding more carbon dioxide, more methane to the atmosphere. And so we're warming the atmosphere above levels that are there naturally. And so that's what we're actually concerned about. So when you hear the greenhouse effect, you have to understand there's a natural greenhouse effect, which is due to the natural levels of carbon dioxide and water vapor in the atmosphere. And then there's an anthropogenic or a man-made greenhouse effect. And that's because of the additional CO2 that we're putting out, which is warming the planet above what its equilibrium level is. So this is all known. So when people say greenhouse effect is still speculative, it's 150 years ago, Tyndall nailed it. Okay, so really nothing has changed 150 years. So we have this natural greenhouse effect, which warms the planet up, and then we have this anthropogenic greenhouse effect, which is the result of the additional CO2 that we're putting out in the atmosphere. So this is a graph of CO2 concentration as a function of time. The red dots are from observations that we made from Mauna Loa in about 1950. So we started measuring CO2 in the atmosphere in 1950, and that's that data right there. These blue curves going back to about 1700 are from ice cores. Okay, and so we can actually reconstruct CO2 levels in the atmosphere going back 800,000 years by looking at ice cores. So how do you do that from an ice core? Well, that's a good question. So if you actually look at ice, so ice that forms in a glacier is not like ice that forms in your freezer. Ice in a glacier forms when snowflakes fall, fall down. Those, snowflakes have lots of, interstitial air pockets. As that snow eventually forms ice, those air pockets actually are locked into the ice. And so ice from a glacier has all these little bubbles in it. Okay? And so what you can do is you can go in and you can extract the air from those bubbles, and that is air that essentially was the state of the atmosphere back at whatever time that ice formed. And so again, we could date ice cores from various ways. So we can go back in time and we can reconstruct the CO2 levels going back, I say, 800,000 years. So this data here is from ice cores, and what it shows you is what we call this pre-industrial level of maybe about 270 parts per million, and that's sort of the background level of CO2 that exists before we started burning carbon. And you can see that we've gone up from there. This actually graph is quite old. We're now actually about 400 parts per million. Okay, so the warming due to this pre-industrial levels is the natural greenhouse effect, which is important for our survival. This additional CO2 we put up here is what we're concerned about today. So what's the impact of that extra CO2 on the climate system? And this is a record going now over the last 4 or 5 years, and you can see CO2 levels increasing. There's an interesting annual cycle here, and what that is the result. In fact, if you look at the Earth, there's more vegetation in the northern hemisphere than the southern hemisphere, and so there's a signal actually of the biological activity in the summer when the plants in the northern hemisphere are photosynthesizing and releasing CO2 into the atmosphere, and then in the winter they're not quite so active. So this annual cycle actually is an indication of the biology that's going on, but you see this long-term trend towards higher and higher CO2 levels, and we've now exceeded this 400 parts per million that we actually did last year, and that's the highest CO2 levels in 800,000 years. So we have data going back 800,000 years, and so the CO2 levels are higher than they've ever been in the last 800,000 years. So that's a rather dubious record, I think, for us as a society. We've actually put more carbon up in the atmosphere that's been there for almost 1 million years. And this is a record there. This is the value here. Al Gore had this visualization in the first movie he made. He had this kind of record. He had one of those lifting kind of ladders that went up, and essentially he had to go way up on this ladder to get to the levels today. Okay. This cycle you see here is actually evidence of ice ages. So CO2 levels tend to be high when there's no ice in the northern hemisphere. When the ice caps have all gone, again, you have more biological activity, and then essentially CO2 levels tend to decrease during the ice age. So these actually are evidence of the ice age cycles. So the last interglacial was about 150,000 years ago. That's the last time the Earth was warm. Then the Earth went into a period of about 100,000 years, so it got colder and colder and colder. And then essentially about 10 or 15,000 years ago, we came out of that last ice age. So again, so 15, 20,000 years ago, there was maybe 3 kilometers of ice above us. And so the CO2 levels started to rise, but now they sort of shot up exponentially. So that really is the human impact on the climate system. That's the CO2 that we put up. And again, we're much higher. This is only about 400,000 years, but again, you've got 800,000 years. We're the highest levels in that period of time. So, Tyndall discovered essentially the greenhouse effect in the 1850s. Arrhenius, a Swedish chemist, estimated if you doubled CO2, you would get a 6-degree increase in surface temperature. This was in 1896. He actually was wrong. He got it wrong by a factor of about 2 or 3. We now call this parameter S. So S is what we call the climate sensitivity parameter, and that tells you how much the average surface temperature will increase if you double CO2. And so one of the first climate models was run in 1967. Very, very simple model. Could probably be run on your iPhone today. That's how much computer power was around it, the kind of state of the art. institutions back in the 1960s, and they estimated that this S parameter was between 1.3 and 2.4 degrees Celsius. So that, again, a very, very simple climate model. That was the prediction. If you look at data, you get a value of S of about 2. So if you look at data going back about 160 years or so, if you plot CO2 versus temperature, you see a nice linear fit here, and that slope is about 2 degrees Celsius. So again, going back into the 1850s, the observations show that as you increase CO2, the temperature will warm by this 2 degrees per doubling of CO2. And today, with the most modern climate models we have, we get essentially the same value that Manabe and Weatherall got 50 years ago. Okay, so when people say climate models are, all fiction, or they're tuned up to give whatever answer the scientists want, it's actually not the case. Okay, climate models, there's still lots of inadequacies in them, but they're getting the basic physics right, which is if you increase CO2, you increase the surface temperature. So that's hard rock solid. Okay, 99.999% of people who work in this field agree with this statement. Okay, so when Pruitt or when Trump say that it's a Chinese invention to, whatever, it's not true. Or when we say scientists are trying to grease their own pockets, it's not true. I mean, this is basic science which has been known for 150 years, and the answer hasn't changed in 150 years. So if you increase CO2, you increase the surface temperature. Okay? So now I really want to show you a little bit about the kind of research that I do. So I've been really fortunate in my life to kind of work all the way around the world, although I've done some work off of Antarctica. I've never actually been there. It's the last place I sort of want to go. But I've worked in the Western Arctic and Greenland, in Nunavut, Mount Logan, Patagonia. If you've ever been to Africa, you know that there's glaciers on Mount Kilimanjaro. There's also 2 other mountains in Africa, Mount Kenya, and also the Rwenzori, which are in Uganda, which also have glaciers at the equator, which is pretty cool. And of course, the reason why there's glaciers at the equator is because, of course, they're so hot that they're actually quite cold. So I was fortunate to climb not Kilimanjaro, but Mount Rwenzori over here in western Uganda, and at the top of the mountain was all this ice, which was kind of cool to do. And also I worked also in the Himalaya. So this is a video of a buoy that we put out into the ocean off of Greenland a few years ago. This is summertime. These waves are about 3 meters high. And so this buoy is about 3 meters high, and so you can see that it kind of goes below, looks like it goes underwater, and then of course that's just a wave crest coming by. You can see there's birds around as well, so even though we're fairly far offshore, the birds are following the boat, and so they're actually out there scavenging. And so we released this buoy in the summertime, so it's about August here, and it survived about 3 months before it finally got destroyed by the really high winds that are there in the wintertime. So this is a video now of a ship. That mast there is 10 meters high. This is a storm in the Iceland Sea. The ship, of course, is going into the wind because that's the only way you can go with a ship. If you go across the wind, you're going to capsize by these big waves. This is about 30 meters per second winds. So the winds are hurricane strength here. And the ship is going towards it. And so these waves are really big. The big one's coming up right now. So we're now at the crest of the wave, and there we go down. Sorry, it's the next one. So here it comes. And then watch this mast will go down. Look at that. Okay. So these are what 10-meter waves look like. I didn't go on this cruise because I don't want to be in 10-meter winds. I sent my students. So what I do is I fly in a plane. So this is a plane actually not going through a very high wind, but essentially we're flying this plane off of Greenland. And so we're flying towards the ice edge. So the ice edge is off in the distance here. We're flying about 100 feet above the ocean in this case here. And you can see these ice floes coming out. And then eventually we're going to come to the ice edge just a second now. And again, you can see the huge contrast. Now suddenly you go from this open water, which is dark, to the very, very bright sea ice sitting here. Okay? Now, the reason why I go on the airplane is that when you're on the airplane, in this case, we were staged out of Reykjavik in Iceland, and we would fly every day to Greenland, fly through these storms, and fly back. And the nice thing is, you've Actually, Tim was with me on this trip. So you'd be out in the plane for about 5 hours. It'd be pretty bumpy when you're down low. Then you get up high, and this plane actually had a microwave on it. And so they served you popcorn and stuff. And then you get back to your hotel and have a nice Thai meal or whatever, and you go and do it the next day. When you're on the boat, when you're on the boat, what have I done? When you're on the boat, you're on the boat for the whole time. So it's not really very good. Sorry. Let's go through here. Yeah, so that's why I don't like to go on the boat, because when you're out in that, you're out there for 6 weeks. It's not like that every day, but most days it's kind of like that. So I actually don't like to go on the ship because it's a bit too rough for me, and I like sort of being able to sleep in a nice bed every night. So the ship is a bit kind of crazy. But that's one of the things we actually do. And so we do that because we want to understand how the ocean and the atmosphere transfer heat back and forth, because that actually impacts both the atmosphere and the ocean. And here's another image. Now this again, we're flying near Greenland. That's an iceberg there. It's probably higher than the plane. And so one of the problems is the pilots, of course, have to make sure they don't run into icebergs as they're flying around low down. That's one of the instruments we use to measure climate parameters on the aircraft, right there. This again is some of the ice in what's called the marginal ice zone. That's right at the edge of the sea ice. And these are little ice flows that they've kind of ripped off the main ice pack. And so it's a really complicated region. It's quite beautiful to look at. All these small little bits of ice floating out of the ocean. This is looking down on an iceberg, which is frozen into the pack ice. That's called pack ice, and that's an iceberg just frozen into the pack ice. So, global warming. What's actually happening? Well, we know that we're increasing levels of CO2 in the atmosphere, and we know that over the last 150 years, as we increase CO2, we've increased our temperature. So going forward, how do we know what's going to happen in the future? Well, we run climate models. So climate models are models that attempt to represent all those processes that happen in the climate system, the transfer of energy between the ocean and the atmosphere, formation of sea ice, all those kinds of things are included in there. And when we run these models, we get these kind of predictions. So there's a certain amount of uncertainty. So this kind of greenish curve here is natural variability. So that says that some years it's cold, some years it's warm, and that's sort of what you'd expect moving forward as to the uncertainty in the temperature. Then we have uncertainty in the climate response. That is essentially how does the climate respond to changing CO2 levels? And that's what this kind of blue area is here. And then we essentially have an uncertainty in how much CO2 is going to be present. Because if we want to make a forecast as to what the temperature is going to be in the year 2100, we need to know how much CO2 is going to be in the atmosphere at 2100. So that requires some assumptions as to what we're going to do. Okay? Are we going to suddenly stop using carbon and equilibrate at some level? Or are we continue to use carbon for the next 100 years at levels that we're using it now? Okay? So there's all those kinds of uncertainty. And so most of the climate models say that over the next 100 years, the temperature will increase somewhere about 2 degrees Celsius. So again, that's true for the whole Earth. The Arctic is warming maybe 3 times as fast as the rest of the Earth, so that means 6-degree warming in the Arctic. It could be upwards of maybe 6 degrees, or it could be 1 degree. Okay? So this band here is really the uncertainty, but the point is it's going to warm. We don't know exactly about how much, but it's definitely going to be warmer in the year 2100 than it is now. Okay? So this is the result of a climate model, actually many climate models, and although they're not perfect, they're by no means inaccurate, and so we're going to see some warming. Whether it's 2 degrees or 4 degrees or 6 degrees, a lot of that actually depends on decisions that we make and our children or the next generation make as to how much carbon they're going to use. Because as I'll show in a minute, if we can reduce our carbon use, we can limit some of the warming that potentially could occur. So maybe we'll actually come down here rather than being up here. But that's really sort of up to us to decide. And that's really why, as citizens, we need to essentially do as much as we can to reduce our use of carbon to minimize the warming that's going to happen. So this is an example of sort of the regional response. So this is under what's called, there's many different scenarios. This is under what's called the RCP 4.5 scenario. And that means that we stabilize CO2 levels. Okay, so we essentially reduce our use of carbon such that in the year 2100, it stabilizes about 550 parts per million. That's about twice what the pre-industrial level is. And so if we stabilize at that level, this essentially is for March, and this is for September. And so we'll see warmings of maybe, especially in the Arctic, maybe 6 degrees Celsius in the Western Arctic will occur in March if we stabilize CO2 levels at 550. Now we're at 400, so again, we're just going to see more warming. Most of the warming occurs actually in the winter. The summer warming is actually not so bad. If we do what's called the business as usual scenario, which means we continue to use carbon as we've used it before, in that case, in the year 2100, we'll have 1,200 parts per million, parts per billion of CO2, which is maybe 3 or 4 times current levels, 3 times current levels. In that case, there, the warming in the Arctic may be upwards of 12 degrees Celsius. Okay, that's a huge warming. And again, that'll have catastrophic impact for the biosystem, for the ecology, and also for people who live in this region. Over most of North America, we'll see a fairly substantial warming in the year 2100. So that's sort of the scenarios that we're looking at. We can minimize our impact of climate warming, or we can in fact see a case where we see huge changes in the climate system. That's really up to us to make that decision that we're going to reduce our use of carbon. So, one of the questions that people say, well, we can't forecast the weather more than a few days in advance. How can you have any confidence in a 100-year forecast? Well, what you have to realize is that the main problem with weather prediction is getting the initial conditions right. What I mean by that is that if I have this clicker here, if I drop it, or if I throw it to the back, the physics is exactly the same. This object is falling under gravity. But the initial conditions are very, very different. Here I'm essentially giving it no initial velocity. Here I'm throwing it. Okay? So the outcome is very, very different. But that's all based on the initial conditions. So one of the hardest problems in weather forecasting is getting the initial conditions right. And because we can't get the initial conditions right, we have some uncertainty in the forecast moving forward. So this is an example. This is from Hurricane Irma. So this is what's called an ensemble forecast. So what we do nowadays is we don't run one weather forecast. We run 100. And we perturb the initial conditions slightly because we don't know what the initial conditions are, and we see what the outcome is. So this essentially is 100 different scenarios. Some have Irma tracking up here, some have Irma tracking over here, and that's sort of the uncertainty in a weather forecast. Because we don't know the initial conditions right, there's a large spread. After a few days, we actually don't know where the hurricane is going to be. And of course with Irma, the classic problem was that the forecast looked like it was going to hit, Miami, and so people moved to the west coast, and Irma actually hit the west coast rather than the east coast. So this is one of the kind of classic problems. But that's a problem with weather forecasting, and it comes because we can't get the initial conditions right. We understand the physics, that's okay. Just like here, I know the physics is just falling under gravity, but it's getting the initial conditions right. And so for a climate model, that doesn't matter, because we don't care what the wiggles are. That's really the weather. We only care about the average. And so whether or not, there can be any scenarios where there's different sort of weather, but with the same mean value. And so with a climate model, we're looking at the means, and that's actually a much easier problem than getting the wiggles right. And so when you run a climate model, you never say, well, on October 31st, the year 2100, the temperature in Guelph will be whatever. We never say that. We say, for the 10-year average, from 2190 to 2100, the temperature will be whatever. So we always kind of look at long-term averages, and that's a much easier problem than getting the wiggles right. So that's why we actually have confidence in a climate model, because the means are easier to get than the wiggles. And for a climate model, you don't care what the wiggles are, you just care what the mean is. And so if anyone ever says, well, why should I believe a climate model when you can't get the weather right? They're two different problems. And you can trust a climate model even if you can't get the weather right more than a few days in advance. So I just want to finish up talking about sea level rise. So again, these are scenarios going forward for sea level rise. So there's kind of a few things that happen when you warm the planet up. The oceans actually expand because they get warmer, and so sea level rise is from that. We also melt land ice, so ice in Greenland and ice in Antarctica melts, and that water flows into the ocean, that rises sea level as well. And so there's a certain amount of uncertainty, but we're probably looking by the year 2100 at maybe half a meter to a meter rise in sea level. Okay? So that means if you have a property on a barrier island on the Gulf Coast of Florida, it probably will be underwater in 100 years from now. Okay? Mar-a-Lago apparently will be underwater by year 2100. So Trump may not care about climate change, but he's going to lose his property. Okay? So that's sort of what's going to happen. And again, that's probably if you think of all the impacts of climate change, it's probably sea level rise which is the most dangerous because there's a huge amount of infrastructure at sea level. And it can, as we saw in Hurricane Sandy in New York and things, even a small increase in sea level, if you put a high tide and a storm surge on top of that, can overwhelm any defenses that we have. And so, for instance, if you look at Bangladesh, today this is the area where sea level is essentially at sea level here. If we see a 1.5 meter increase, this is actually quite a large increase, but essentially 17 million people in Bangladesh would be displaced if sea level rises by 1.5 meters. Where are those 17 million people going to go? I don't know. We had problems selling 50,000 Syrian refugees. What are we going to do with 17 million climate refugees from Bangladesh? It's a really, really big problem. And I think people who look forward, who are paid to look forward in time, look at conflict. This is one of the big sources of conflict in the second half of the 21st century are going to be climate refugees, people who need somewhere to go. Where are they going to go? So again, it is not in our own interest to reduce climate change. For our own purposes, it's important to do that because it's going to minimize pressures like migrations due to changing sea level. This is a map actually of Vancouver. This I think is a 2 meter sea level rise. Everywhere this blue here will be underwater if sea level rises by 2 meters, and that's actually Vancouver Airport right there. So all the infrastructure in Vancouver Airport will be underwater if sea level rises by 2 meters. Okay? Billions and billions of dollars in infrastructure will be lost. Okay? And that's the sort of one of the things you have to kind of worry about. Can we stop? Can we minimize this magnitude? Well, these are actually our 3 curves showing essentially, these are now emissions. These aren't CO2 levels in the atmosphere, but there are emissions of CO2. And these are essentially 3 curves, which will give us a 75% chance of limiting global warming to about 2 degrees globally and maybe 4 degrees in the Arctic. Okay? So, if in the year 2120 we essentially have our peak emissions of CO2, and over the next 20 years we reduce our sea level, our CO2 emissions to 0. We go from essentially a fully carbon economy to a carbonless economy, then we have a 75% chance of minimizing the warming to 2 degrees Celsius. Okay? That's a pretty tall order to change our whole economy in 20 years or so. That's what we sort of have to do to keep the warming under 2 degrees. I think that's probably unrealistic. And so we're probably looking at least 2 degrees warming, which Paris is trying to keep us to 1.5. I think that's really, really optimistic. We require huge transformations in our whole economy to do that. But that's what we have to do to keep the magnitude under 2 degrees. So I think it's very, very hard to do that. So just to conclude then, so the climate is always changing. People who say, yeah, the climate's changing, we don't have to worry about global warming because the climate's always changing. It's true. It is always changing. 55 million years ago, the Earth was really, really warm. So why worry about it? Well, probably, there were lots of it. There was no sea ice, for instance, 55 million years ago. And so, there were no polar bears, whatever. So, the Earth was warm then, sure, but we're dealing in a different system here. And so I think we have to worry about that. Okay? And so there's sort of the main parameters that control the surface temperature are obviously how much solar radiation we get from the sun, and then things like the greenhouse gases. And again, we've known about the greenhouse gas for 150 years, and we sort of understand the physics of that quite well. And so really, so many of my colleagues who work in, do experiments, they have a rather simpler job than I do. So they can do an experiment in their lab 20 times, controlling for everything, and get very, very accurate results. I really can't do that because I'm working with a climate system, and there's really only one of them. And I can't, for instance, say, okay, I'm going to back up time and see what happens if I do something different. So I don't have that control. Only thing I can do is run a climate model to see what's happening. So we really feel like have only one experiment running. And we started an experiment about 150 years ago. We said, what would happen if we increase the level of CO2 in the atmosphere? Okay? And so we've been doing that. We started burning fossil fuels. We're about halfway through that experiment now. We'll know the answer in the year 2100. Okay? We have predictions, as to what the climate models say. But in 50 years, Timothy, we'll know the answer to that experiment. Okay? The problem is that unlike my colleagues, I can't go back and rerun the experiment and say, maybe that's not a good idea, right? Because there's only one planet, okay? And so we really have to be a really good steward of that one planet, because it's the only one that we have, okay? And so we're running this big experiment. We'll know the answer in 50 years. We sort of know what the answer will be, and it's probably not a really good answer. And so we really need to do as much as we can now to minimize the warming that is going to happen if we continue to reduce our carbon. Okay? So I thank you. I want to end on a kind of negative note. This is actually a beautiful image. So again, the Earth, the climate system is really beautiful. This is Greenland. So this is all sea ice in the foreground here. And these are some of the glaciers in Greenland. And this is in the wintertime. And that's actually one of these big fjords that goes deep into the ice core here. And so I was fortunate 10 years ago to be flying in this region doing experiments. And it's just the Earth is just so beautiful when you get a chance to look at it anywhere you go in the Earth. And again, I think it's really important that we are good stewards of this wonderful resource that we have. So thank you very much, and I'm happy to answer any questions that you have.